Thanks, Matt. So hi, everyone. Today I'm going to be talking about our paper with my co-authors, Nima, Rod, and Amin. So let's just go ahead and start. So let me just start by telling you about the Bayesian selection problem. So in that setting, we usually have a sequence of n elements arriving. They're arriving in a known and arbitrary order. And each element has a value, which initially we don't know. But we know that each of these values is drawn from a known distribution. In each step of time, whenever a new element arrives, it reveals its value to us. And as an online player, we have to decide whether to keep that element or discard it. If we try to keep that element, it means that this is reversible, meaning that we cannot later drop it. And if we try to discard it, then we cannot come back to it and pick it later on. So the objective of the online player is to maximize the sum of the picked values. And of course, there is a constraint on the subset of elements that an online player can pick. These constraints are given by Matroid, which specifies what subsets of elements are acceptable and which subsets are not. So this is a very simple model, very well-known model, and it has been studied extensively in the literature. This was first studied by Kleinberg and Weinberg in 2012, where they showed there exists a 1/2 approximation for compared to the optimum offline policy, and they showed that this is tight. So the question is this the best we can do? Like, because they showed already that there's a 1/2 approximation and this is tight, what else can we achieve? And what we do here is that we move the benchmark from the optimum offline to the optimum online, and then ask the question again, what's the best possible approximation algorithm that we can get? And in this talk, I'm going to tell you about our results, which we provide a p-task for a subclass of laminar matroids, when the subset of constraints are laminar. So let me just start by telling you about what a laminar matroid is. You can think of a laminar matroid as a rooted tree. Each node in the tree has a number written on it, which is the maximum number of leaves that we can pick from under it. And basically, in this picture, you can think of these pink nodes as the arriving elements, and the blue nodes are the constraints imposed on the subset of acceptable elements. Looking at this laminar matrix structure, how can we solve for the optimum online policy? One way is to use dynamic programming. Of course, if you want to use dynamic programming, the size of our dynamic programming table will be exponential, which will be proportional to the number of states of the problem. We can actually write down that dynamic program as an LP, which has exponential size. In this LP, each variable will correspond to a state of the problem, and each state of the problem captures which element is arriving, what's the value of the arriving elements, and what subset of elements I've picked so far. The constraints of the LP will correspond to the Bellman equations of the dynamic program. Well, of course, this is a very large linear program, and we cannot solve this in polynomial time. So what can we do? Maybe we can relax this linear program to make it polynomial time solvable. So what we do is that we relax this linear program, and we call this relaxation Ex-ante Relaxation. In this relaxed version of the linear program, each variable of the LP corresponds to an element, corresponds to the probability of picking each element, conditional on its value. This is a polynomial time solvable linear program, but of course, solving this linear program will not give us necessarily a feasible online policy. So here we have two ends of a spectrum. On one end, we have an exponential size dynamic program, or LP, that if we solve, we get the optimal online policy, but we cannot solve it. On the other end, we have a polynomial size linear program that we can solve, but will not give us a feasible online policy. It will just give us a fractional solution that satisfies the constraints in expectation. So the idea is to use these two linear programs together to get something better. So basically, our idea is that we mark each node in our laminar matroid as either small or big. If a node is marked as small, we consider that node and all the nodes under it as small subproblem. And for the small subproblems, we write down the constraints of the exponential size LP for feasible NA solutions. For the large constraints, we just write down the ex-ante constraints of the relaxed LP. And we also make sure to do our markings in a way that makes this new linear program solvable in polynomial time. So if we write down such a linear program, the solution of the linear program will correspond to an online policy which is not necessarily feasible, but it satisfies the small subproblem constraints exactly, but only satisfies the large constraints in expectation. So to tell you what exactly I mean is consider an arriving element. Each element that arrives, we will detect the small subproblem that the element belongs to, and then we run the feasible online policy found by the LP for that small subproblem to decide whether to keep that element or drop it. In this way, all the big constraints will be satisfied in expectation. All the small subproblem constraints will be satisfied exactly. So far I've told you how we can get in polynomial time, which I will get into more details soon. An online policy that is a relaxation of the optimal online policy, meaning that it will achieve in expectation more value, and but it's not necessarily feasible. It's only feasible in expectation. Next, I will tell you how we can turn that into a feasible online policy, and later I will analyze that feasible online policy to show that the performance is very close to the optimal online policy, and that will show that we can get a p-TAS compared to optimal online. So how do we turn the online policy that we have into a feasible online policy? So basically, the idea is very simple. The idea is whenever a new element arrives, and I know by picking that element, some constraint will be violated, I will just drop that element. I will not pick it, even if the policy tells me to. But to make sure that this new online policy, which is feasible, gets a performance guarantee very close to the optimum online, what I do is I scale down the large capacity constraints by 1 minus epsilon. And I do the same. By scaling down, you should remember that we don't penalize the performance of the online policy by much. It's just penalized by 1 minus epsilon. But as I told you before, the large capacity constraints are satisfied in expectation. And here the expectation is at most 1 minus epsilon times the large capacity constraints. So if I can show that we have some sort of concentration around how many leaves I pick from under each large constraint, then I can bound the probability of constraint violation. So imagine a new element arriving. That element is inside a bunch of inside a bunch of constraints. For example, in this picture, the arriving element is that green node, and it's inside 3 other constraints. 2 of those constraints these are all the green nodes. 2 of those are large, and 1 of them is small. We know that the small constraint will be satisfied pointwise, but the large constraints will be satisfied in expectation. So if I can bound the probability of one of the large constraints getting violated, then by union bound, I can bound the probability of any of these constraints being violated. And that will give me my p-TAS, basically. So I'm gonna now tell you about 2 different approaches that can help us get some sort of concentration around the mean for large capacity constraints. 2 properties of the laminar matroid that if they hold, we have some concentration. So the first property is to have a constant depth. if our laminar structure has constant depth, I can do my markings in a smart way to make sure that we have concentration. What I mean by that is I define a threshold for each level of the tree. That threshold, so in each level, all the capacity constraints that are larger than the threshold are considered big. All the capacity constraints that are smaller than the threshold are considered small. And as I move down the tree, this threshold gets multiplied by delta. And delta is a number smaller than 1. What this does is this kind of creates a separation between the capacity of different levels. And this separation will allow me to use Chernoff bounds to bound the probability of the number of elements picked being greater than the large capacity constraint. Of course, for this to hold, you have to remember that if you consider the number of elements picked from each small subproblem, these numbers are independent. And that plus the separation will allow me to use Chernoff bounds. And it turns out this delta that I pick also depends on L, the depth of the laminar tree, which is why I needed to be constant for us to get a polynomial time solvable linear program. The second way that I can make sure I have concentration is to prove within each, so as I already argued, the number of elements picked from each subproblem are independent. But if I can somehow show that the allocation variables within each subproblem are negatively dependent, then I can again use Chernoff bound to bound the probability of a large constraint being violated. And of course, this negative dependency does not usually hold in feasible online policies. For example, here is an example of a laminar structure where the optimum online policy for this example, we don't have negative dependence between elements E1 and E2. And here I'm assuming that the elements arrive from E1, E2, E3, E4, and then E5. So the question is, since we don't generally have negative dependence for the online policies, how can we make sure that we have negative dependence? What structure does the laminar matroid has to have to ensure negative dependence? And for example, in our paper, we show that if our laminar matroid is nested, and by nested, I mean if you have, if each node in the laminar structure except the root has all of its children to be leaves except at most one, then in that case, I call the laminar structure nested. And we show that if the laminar structure is nested, then we can actually prove that we have negative dependence. Of course, here we have this negative dependency gives us many nice properties. For example, we can show that each of these subproblems is solvable in polynomial time. And the subproblem is like from second level all the way to the bottom of the tree. And so what basically we prove in our paper is if we have a nested structure, and if items arrive from deep to shallow, then we can prove that we have negative dependency. And it's provable by an induction argument. So finally, to get a concentration, we remember K is the large capacity constraint on the top. We divide the analysis into two cases. If K is less than some constant, I just solve the exponential sized linear program, but because of the constant depth, because of the constant K, I can solve it in polynomial time. If it's larger than this constant, then by Chernoff bound, I can again bound the probability of constraint violation by epsilon, which will give me my p-test. So far I've talked about like the technical parts. Let me just tell you some applications about these problems. So I told you about two different approaches to get our results and two different properties of the laminar structure. So for the case of constant depth laminar matroid, you can think of selling flight itineraries. So consider like a person that wants to travel to different locations around the world, and each itinerary corresponds to a series of flights that go from her city to the destination. And of course, to go along these hops on the middle of the trip, each of these hops has some capacity, and each itinerary takes some capacity from each hop. And then we want the flights to be to satisfy all the capacity constraints, but also we want to have as many, accommodate as many trips as possible. For the case of nested laminar, consider a firm that sells a couple of different lines of different products, and these products have inventory replenishment, and we might also have some shipping capacity constraints. And it's we show that it's very easy to capture that scenario with our nested laminar structure. So in this talk, I talked about something that we did, which was we took a very well-known problem that was profit inequality basic for Matroid structures, which compared the algorithm to optimum offline, and we changed our benchmark from optimum offline to optimum online, and then we derived a p-task for a special case of matroids in laminar matroids, basically. So I think it would be an interesting direction to see if we can generalize our results to other more general structures, or even, I don't know, maybe do this problem in other scenarios where the benchmark is optimum offline, which might sometimes be unreachable by any online algorithm, and see if we can get a better bound by comparing to the optimum online. Thank you.